Okay, in this video we're going to talk about a very important reaction on aldehydes and ketones that's called the Aldol condensation. Now, aldol condensation is a reaction that involves aldehydes and ketones, and the primary requirement is they must have alpha hydrogens. So let's understand what is an alpha hydrogen. Now this is the functional group of an aldehyde or a ketone. If it is an aldehyde, there's a hydrogen here. If it is ketone, there is an alkyl or an aryl group here. Now the carbon that is attached to the functional group, this carbonyl group, this is called as the alpha carbon. This is the alpha carbon, and the atoms or groups attached to the alpha carbon are supposed to be alpha groups. And in this case, if a hydrogen is attached to the alpha carbon, we call it alpha hydrogen. So the important requirement for an aldol condensation reaction is that you use an aldehyde or a ketone, and the aldehyde or a ketone must have the alpha hydrogen, at least one alpha hydrogen. Now when this happens, two molecules of an aldehyde or a ketone having alpha hydrogen, they are reacted with dilute base. Now this is dilute, and the product obtained is a alpha beta unsaturated aldehyde or a ketone, and in this case it's going to be an aldehyde because we started with an aldehyde. So two molecules of acetaldehyde are converted to alpha. This is the beta carbon, sorry, let's erase this. This is the beta carbon and this is the alpha carbon. So this is the alpha beta unsaturated aldehyde, and if you use a ketone, it's going to be giving you a ketone. Now the reaction is primarily called aldol because aldehydes are more reactive than ketones, so it is observed that aldehydes reacts faster than ketones, more product yield, better yield, and the product of the aldol reaction, you see, first this forms a product which is an addition product, which is called the beta hydroxy aldehyde. Now when you have the beta hydroxy aldehyde, this is an aldol. It's called an aldehyde and an alcohol. So this is the aldol. Now conversion of the aldehyde to this part is known as aldol reaction, and this on heating loses a molecule of water because this double bond is in conjugation with the double bond of the aldehyde, and that makes the conjugation happen and therefore resonance. So the product is more stable. So mere heating would convert the aldol into the alpha beta unsaturated aldehyde or ketone. So let's understand what is the mechanism for this reaction. Now step 1, we have the aldehyde with the alpha hydrogen reacting with this is the dilute base. Now OH minus is a good base, a strong base, and the alpha hydrogens of aldehydes and ketones are weakly acidic. The hydroxide is able to draw the proton out of this, and we get a carbon anion. Now this carbon anion is stable because of resonance, and resonance with the enolate, and the enolate is more stable than this carbon because the negative charge is on O. So this resonance of the alpha carbon anion with the double bond O makes the alpha hydrogens acidic, weakly acidic. So the OH minus is able to draw out the proton and convert it into a carbon anion with the loss of water. In step 2, another molecule of aldehyde, which so far has not reacted with the base, meets the carbon anion, and we can use the enolate ion here since it is the most contributing structure. Now this bond moves to the carbon, this moves to this carbon, the carbon attacks, and this bond moves to O, and you get CH3 CO negative H CH2 C double bond O H. So this is the product formed when these two react. Okay, now one might wonder, why isn't the O reacting with the carbon since the minus resides on O more? Well, a carbon-carbon bond is a very strong bond, and the property of catenation is majorly due to the fact that carbon-carbon overlap is a very effective overlap. Therefore, the system always moves in a direction which tries to give the most stable product. Because if this O minus were to attack here, you will not get that much of a stable product as probably what you get now, because the final product is not going to be conjugated. Now this is step 2, so let's move to step 3. In step 3, we will be having the product of step 2, accepting a proton from the solvent. Solvent is water. So the solvent is H2O. It takes a proton from here and is able to give you CHOH CH2 C double bond O H. So that makes this proton transfer happen, because water is a stronger acid than an alcohol. Water is able to give the proton, and you release the hydroxide. So hydroxide got used up in the first step, it got released in the last step, that is base-catalyzed. Now this is the aldol. So this is the aldol reaction up to this point. Now when you heat this, step 4, so in step 4 you heat the aldol product, and on heating it loses water, even though generally when we want to dehydrate an alcohol we add an acid to protonate this and then remove water. Here we don't need to do that because the double bond is conjugated with the aldehyde double bond, the carbonyl carbon double bond, and that makes the reaction happen on its own by mere heating. So that is your alpha beta unsaturated aldehyde. Okay. Now this kind of an aldol reaction, this is the aldol condensation. So up to from here to here, this is aldol condensation. From the beginning up to the step 3, it is aldol reaction. Now in case we were to use a ketone, that means if we had two R groups on either side, and if one group who happens to be the phenyl group, for example, if suppose I were to do an aldol type condensation in acetophenone, this is acetophenone. Now here the aldol condensation product, it will not stop at the aldol state at all. It will directly go to this. It will directly form PH CH CH3 double bond CH2 C double bond O pH. Now here the product obtained is a direct alpha beta unsaturated product. One doesn't even have to heat it. You cannot stop this reaction at the aldol type of stage, mainly because this double bond is in conjugation with the double bond of the phenyl ring as well. So this makes this reaction happen in one go. So you start from here and you end up reaching the last point, the alpha beta unsaturated ketone in this particular case. Now, it's also possible to do the aldol reaction, aldol condensation, in the presence of an acid. It need not be always base catalyzed. For example, if you take the aldehyde again, and this time I introduce an acid to it, I add H plus. So the carbonyl oxygen has a tendency to pick up that because it's got a lone pair. So that is going to pick up the H plus. Now this bond is in favor of shifting towards O since there is a plus there, and there's no plus on oxygen. So this is the OH, H, and there's a positive here. Now this is one molecule of an aldehyde. Now the other molecule of an aldehyde, we are going to use the enol form of that. Now as you know that aldehydes and ketones show keto-enol tautomerism. So this is the enol form of another aldehyde. Okay, so this lone pair is going to attack here. The bond moves to carbon and a carbon attacks here, and this is the rate determining step, and you get CH3COH, H, CH2, C double bond OH positive, H. And this is step 1, this is the step 2, and in step 3 this is going to lose the proton, CH2, C double bond O, H positive, H. This is going to lose a proton, and you get the aldol product, which now, since you have an acid present here, would very easily dehydrate, and of course you need to heat it a bit, and this is going to get converted to the alpha beta unsaturated aldehyde or ketone. Now I forgot to mention something. In the case of the base catalyzed, the second step where the carbonyl attack, this is the rate determining step, and the same way in this case this is the rate determining step, the attack of the carbon on the electrophilic carbon. So in both cases this is the rate determining step. So the advantage of this knowledge of the rate determining step means that if I were to use two different compounds, two different aldehydes, or one aldehyde or a ketone, or two different ketones, then we know that that carbon will get attacked whose carbon is more electrophilic. That means if there are two different aldehydes or ketones and one of them has a more electrophilic carbon than the other, then the more electrophilic carbon has a higher tendency to get attacked by the carbon of the other molecule, and that we'll discuss in the next video. That would be the Claisen-Schmidt reaction. Thank you.